Understand? So copy on write allows both the parent and child process to initially share the same pages in memory. So whenever sometimes in the main program you will have some subprogram also, right? So main process I will call it as parent process. The subprogram I will call it as child process. So whatever the parent process will use the data that can be shared with the child process also. So initially same pages will be shared between both the parent and the child. So if either process modifies a shared page, say for example, if parent will allow the child the process to modify the page, if the page is modified, then only that particular page is going to be copied. If the page is not modified, then we will not copy that page. So COW means here copy on write allows more efficient process creation as only modified pages are copied. So we are not wasting time in copying all the pages. Whichever the page is shared, whichever the page we are going to modify it, only that particular page we are going to copy it, otherwise we will not copy such pages. So that is how we are going to reduce the time. That means what? COW provides efficient process. That means with less time it completes more process. So free pages are allocated from a pool of zeroed out pages. So whichever the page is free, that can be checked with the some table is there, I mean pool is there. Zeroed out pages we are going to find out. That you will understand with the algorithms. So page replacement concept we must know before going to the algorithms. So next class I can start algorithms. So before that let us complete this concept, students. Very simple. So since it is a continuation of the today's session topic, I want to complete today itself. So instead of doing revision, let us complete in today's session. So coming to the first step here, prevent over allocation of memory by modifying page fault service routine to include page replacement. So we know that we are going to allocate the memory space by modifying this page fault service, but don't do over allocation. The overhead should be reduced. I cannot say that overhead is 0. No, overhead is there because we are whichever the page we are finding it as fault, that we are going to we reset and restart, right? So anyway overhead is there, but try to avoid the overhead. It should be minimum. So how is that I will do? I will go with some modified bit, which is also known as dirty bit, to reduce the overhead of page transfer. Number of copying should be less. So only modified pages I am going to copy it to the disk. That is going to be written to the disk. So with the help of COW concept. So page replacement completes separation between logical and physical memory. So this concept will complete the method of what? The separation between. The virtual memory means what? Separation of logical and physical. How we are going to do? With the help of the concept called page replacement. So here large virtual memory can be provided on a smaller physical memory. So I have large set of code in a logical memory, but I'll pick only the random, whichever currently I want to execute, I'll pick that, I'll put it in a physical memory. So physical memory, I'll always call it as smaller area than the logical memory. So there is an example here, students. So you can say I have user 1 with some set of code with some logical memory. I have user 2 with some set of code with logical memory. So I have a page table with respect to user 1 logical memory and page table with respect to user 2 logical memory. So here see I have program counter to hold the address of the instruction node M to be executed. I also have some pages like H, J, M. Same way here I have some pages A, B, D, E. See here which are the pages is valid here. I mean free here, which are the frames from the physical memory. Frame 3 is valid, frame 4 is valid, frame 5 is valid. Same way frame 6 is valid from the with respect to process 2, and 2 is valid and 7 is valid. So page table, with the help of page table for user 1 and page table for user 2, let us map it from logical to physical here. Here I have some set of code, say D. D is from which memory, logical memory of process 2, where it is stored in 2, because 2 is valid bit shown with respect to this. Same way H. H is stored in slot 3. 3 is with respect to process 1. Since 3 is valid, H is stored. Same way load M. Load M is with respect to process 1. So process 1 I have 4 as a valid bit. So frame 3 is free, 4 is free. I am going to store load M. Same way J, A, E. J is with respect to which one? Again user 1. So user 1, which are the few 5 is valid here, so you can store. Again A is from user 2. User 2, which are the valid bits? You have 6 valid bit is there, you can store. Again E is with respect to what? User 2 logical memory. So here you also have 7 as valid, you can store E in the 7th frame. So that is how you are going to store. Some frames, say for example B I could not find any free frame here. So because I have only 1, 2, 3, 4, 5, 6 valid frames. So others are invalid. Maybe the 0, maybe 1 I have not used. Now 1 may be invalid here. I don't know. Maybe whichever I have not used. Maybe 8th one may be invalid. I don't know. So based on the valid or invalid, so sometimes I am unable to store all these codes which I want to execute. So that you can temporarily store onto the disk. And if you are finished with loadem, you can also swap it out to disk.